Hello everyone, this is the sixth video in the series of lectures on linear algebra. So in this video, I'll take up the topic elementary operations or elementary transformation. Before going into elementary transformations, let's see what is the connection between vectors and matrices. So they are very much interlinked. Why we have to use matrices when we are representing few vectors? Let's see that. So every vector having n tuples can be represented as a column matrix of size n by 1. This we know very well. So suppose if you have a vector which belongs to Rn, which is having n tuples, then usually we write it as a column vector x1, x2, so on up to xn, or x1, x2, so on up to xn transpose. So this is a matrix representation of the same vector that's of size n by 1. This is also of size n by 1. We can represent in either way. Suppose if you have a set of vectors like S is equal to v1, v2, so on up to vn, we can form a matrix representing these vectors. Let's see how. Consider one example. S is equal to 1, 2, 1, minus 1, 0, 1, 1, 1, 4. These are vectors in R cube because they are having three coordinates and there are three vectors given. Whenever you have coordinates, you have to see the number of coordinates. If there are three coordinates, it's a vector in R cube. 4 coordinates, it's a vector in R power 4. Now, suppose if you want to perform any operations on these vectors, like if three vectors are given to you, you want to check are they linearly independent. One method is you have to write alpha v1 plus alpha v2 plus alpha 3v3 which is equal to 0. Then that linear equation equated to 0 implies all alpha i's should be equal to 0. That you have to establish to say that it is linearly independent. Is that the only one way? We have to check it out. To make our simplifications easier, so we can go with the help of matrices. Same vectors I can write in the form of a matrix. These vectors are represented using the rows of a matrix like 1, 2, 1. Second row is minus 1, 0. Third row is 1, 1, 4. You can write either in rows or columns. It is up to you. It all depends on what is the task given to you. If you want to find out whether they are linearly independent or if you want to find out whether spanning set row space of the given vector and the column space of the given vectors or the space spanned by given vectors, there are many applications of these matrices. So what I'm doing here is the same set of vectors, I'm writing it in the matrix form. So after writing it in the matrix form, what happens is whatever you want to check on these three vectors, I will check it on the matrix A. So if there are certain rules to do that, so if that satisfies for the matrix A, then I can come to the conclusion for the given set of vectors. That's why the name linear algebra. We are doing algebra, some algebra, using some tool. Here matrix is a tool. Similarly, if you have another set, S is equal to 1, 2, 2, 1, 1, minus 1. So in this case also, I can have a matrix for this. 1, 2, I am representing the matrix as rows of the vectors as rows of this matrix. 2, 1, 1, minus 1. You can write it as columns also. 1, 2, 2, 1, 1, minus 1. So if you represent it as columns, then size of the matrix changes. Here size was 3 by 2, here size is 2 by 3. So it all depends in which way you want to represent it, either rows or columns. So it depends on the situation, what we are going to do. But most of the time we'll be going with the as rows. That will be easier because one method if you practice, it will be easier to remember throughout. So for example, in your elementary algebra, suppose if there is any statement problem like as if you add 2 to square of any number, then the answer is 16 or something. It's given. So then in that case, we'll take square of any number. We don't know the number. Let us take it as x. Then add 2 to that. And they had given that it becomes 18. Then what is that number? So The same problem is written in this way, x square plus 2 equal to 18 in the equation form. This is what algebraic expression, algebra it is. So same way, here the set of vectors given to you, we are transforming the same vectors into a matrix form so that we can perform some algebra on the matrix instead of doing it with the vectors. So the rows represents those vectors or columns represents those vectors. So there is interconnection between these vectors and the matrix, rows or columns of a matrix. So that helps you to do most of the operations or calculations easier and simpler. So why we use these matrices? We use these matrices to check whether the given vectors are linearly independent. One is that method I told you, alpha 1 plus v1 alpha 2 v2 plus so on up to equal to 0. Then you will get a system of equations, solving that system of equation. That method is also there. But there is one more method also. Using the matrix, we can reduce it to row echelon form or reduced row echelon form, and we can check how many linearly independent rows or columns exist, and we can come to the conclusion. I will explain you in the next videos how to do that. The second one is find the dimension of the space spanned by the given vector. Suppose if you have given with the 3 vectors and those 3 vectors will span and they will create a new set of vectors, that is linear span or spanning set. If you want to find the dimension of that spanning set space, then you have to go with this concept of matrices. Find a basis for that linear span of given vectors, whether the given vector belong to the span of the vectors. And to solve system of equations, in all these cases will transfer the given system of equations into its matrix equation, and we will perform. That's why the name algebra I told you. And it is linear algebra because there is one more concept in this course, that is all about linear transformation. Linear algebra that revolves around linear transformations more than these vectors. But vector spaces are all basics. So if you study all those basics, then only we can jump into the linear transformations. So they are the basic entities in learning of linear algebra. So you should remember what is vector space, what is subspace, and what are the linear independent and what are linear dependent vectors, and so on. I had made videos on that. So if you want to learn this video in particular, you have to see all the previous videos so that you will get basic idea about what other previous concepts are. I hope you have watched those videos. If you have not watched those videos, please go back to the playlist, and I have a playlist linear algebra. I had segregated all those videos into that playlist linear algebra, so please watch those videos. So now let's see what are these elementary operations. I told you matrix is a tool to perform the operations on those vectors. We will be converting into matrix and we will be doing all those operations on the matrix. Now what kind of operations you can perform on the matrix? So they are nothing but elementary operations. They are also called as elementary transformation. So linear transformation is, I told you, another concept in linear algebra. So that is very, very essential, and the main important concept in linear algebra is linear transformation. Now for the time being, what I'll do is I'll explain all these elementary operations as like interchanging rows or scalar multiplication. But when you come to the linear transformation, so you will understand how they will transform the entire space or entire plane into a new system, so that you will understand better when you take up the topic linear transformation. And in the case of linear transformation, every matrix, it represents a linear transformation. So that I'll explain when I come to the topic linear transformation. Let's see what are the elementary operations. For the time being, let's refrain ourselves to the concepts of elementary operations rather than going to the transformations. Once I take up the linear transformations topic, I'll definitely come back to these elementary transformations. So first elementary transformation or operation is interchanging any two rows or any two columns, any two rows or any two columns. Like Ri is interchanged with Rj or Ci is interchanged with Cj. Second operation is multiplying a non-zero scalar to any row or column. So let's see with the example. Instead of reading out all these operations, I will take one example. Take a matrix 2, 1, 0, minus 1. I am going to interchange first row and second row. So first row comes, second row comes up, first row goes down, 0, minus 1, 2, 1. So this is one elementary operation, first elementary operation, where we are interchanging rows. You can interchange columns also, like 1 minus 1, 2, 0. I have interchanged C1 with C2. This is the first operation. Now the second operation is you can multiply any row by a non-zero scalar. So suppose, see here, this is the given matrix. I am multiplying the first row, this is first row, by the scalar 2. So then what happens? 2 minus 2, 0. And there is no change in the second row. Only the first row changes. It becomes 2 times that of the first row. So 2 minus 2, 0. This is the second operation. Third operation is that, elementary operation is that, if you have any matrix, multiply any row by a scalar and add it to some other row. So in that case, only the row which to which you are adding the scalar multiple of other row gets changed, not this row. To R1, R2 changes to R2 plus 2R1. So in this case, R1 won't change, only R2 changes. We are scaling the one row and we are directly adding it to the next row. So here 5 minus 1 remains same. There is no change. Now we are changing second row in such a way that, see, R2, first element is 3 plus 2 into the corresponding element of R1, that is 5. 3 plus 10, that is 13. And similarly, 2 plus 2 into minus 1, that is 2 minus 2, it is equal to 0. So, and these two are equivalent matrices. They are not equal matrices because the entries are different. But they represent equivalent matrices. So these are the operations. Similarly, you can have C1 changes to Ci changes to Ci plus K Cj, and similarly Ci changes to K into Ci. So in the case of columns, so totally there are 6 elementary operations, 3 corresponding to rows and 3 corresponding to columns. Why we need all these elementary operations, I will tell you. That is because we want row echelon form and reduced row echelon form and normal form of the given matrix. I will make a separate video for what is row echelon form, what is reduced row echelon form, and what is normal form. So just keep in mind now for the time being that these elementary, there are 3 elementary operations, row operations. They are interchanging the rows, multiplying a scalar to any row, or third operation is multiplying a scalar to any row and adding that row to some other row. Similarly, 3 more column operations. Now let's see what are equivalent matrices. 2 matrices are said to be equivalent if one is obtained from the other by applying a sequence of elementary operations. So you may have, here I applied only one elementary operation. You may have sequence of elementary operations. So this matrix and this matrix both are equivalent because they are obtained from the original matrix by applying some elementary operations. So elementary matrices, these are nothing but is the one which is obtained by applying any one elementary operation on identity matrix. Say for example, you have an identity 1 0 0 1. This is identity matrix of order 2. So if I apply the operation R1 is interchanged with R2, so in that case 0 1 1 0. So this is elementary matrix. On the identity matrix you have to apply only one elementary operation, then that becomes elementary matrix. See, there are other. Suppose if you have applied that scaling 1 0 0 1 2 0 0 1. So the first row gets scaled. So 2 0 0 1. This is also elementary matrix. If you have added some other row to other row, in that case 1 0 2 1, I have added here R2 plus 2 into R1. So in that case this is also an elementary matrix. So applying elementary row operation on a matrix is same as left multiplying by elementary matrix, and column operation is same as right multiplying by elementary matrix. Suppose you have a matrix A. Okay, I want to interchange first row and the second row, minus 1 3 1 2 here. So this is the new matrix obtained after applying this particular operation. So instead of doing like this, we can directly apply the same operation on the identity matrix, that is interchanging the rows of identity matrix. It becomes 0 1 1 0. Then left multiplying this elementary matrix to the left of the given matrix A. So if you do that, then you are going to get the same thing. Similarly, in the case of column operations, if you are interchanging 2 columns, you will get a new matrix as 2, 3, 1, minus 1. It is same as right multiplying the 1, 0, 0, 1 you had. Interchange the columns of 0, 1, 1, 0. Now, right multiply the given matrix with this elementary matrix. It will give you the same answer. So, row operation means left multiplication of the elementary matrix to the given matrix, and column operation is nothing but right multiplication of the elementary matrix to the given matrix. So this is all about the elementary operations. And in the next video, I will be sharing you why all these elementary matrices are required, and what are the applications of these elementary operations that I'll share in the next video. Thank you for watching.